Welcome to the carbon valence, hybridization, and bond angles simulation. Today you will learn the fundamentals of how carbon forms chemical bonds with other atoms, and how this is connected with organic chemistry, the foundation for all life. This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch the play mode. If you disable the sound effects, the lab pad will slide up whenever there are instructions to read. You can select what type of audio you prefer. Deselecting any of the options will mute that option. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you've played a Labster simulation? Perfect, then let's get started with your first mission. I heard Simon wants to talk to you. Let's go see what he wants.
Hey, thanks for coming by. I've just started on this chemistry course. It's super interesting how chemistry is involved in almost everything, but I'm also finding some of the topics really challenging. There's a lot of material on carbon orbitals, hybridization and bond angles, and I can't seem to make sense of it. Could you look into those topics and help me figure them out? Sweet, thanks a lot. I'll see you later then. Now I need to get back to my books.
It sounds like Simon's dealing with some tricky topics. Let's dig into them and see if you can get him sorted. Pick up a lab coat from one of the lockers to get started. Interact with the lab pad. From carbon bonds are often related to organic chemistry. But what makes organic chemistry so interesting? Have a look at the screen on the wall to your right. Look at the image on the screen. What do the three images have in common? Exactly. The backbone common to DNA, sugar, and coal is carbon. DNA is present in all living cells, and both sugar and coal are produced from living organisms too. Did you know that you are actually 18% carbon? Because carbon is the backbone element for life, the study of carbon-hydrogen-based compounds is called organic chemistry. Buckle up, you're about to start a fascinating journey into carbon bonds and organic chemistry. Go to Hollow Table 2. Here you can see a methane molecule, one of the simplest organic compounds. In the 3D models, black represents carbon and white represents hydrogen. But why are carbon and hydrogen bonded in the way they are? Let's look into the bonds of carbon in this atomic animation. The carbon atom has 6 electrons. These electrons have the following orbital configuration: 1s2, 2s2, 2p2. This means that there are 2 electrons in the inner 1s subshell, 2 electrons in the 2s subshell, and 2 electrons in the 2p subshell. The 2 electrons in the 1s subshell are not of interest in organic chemistry, so we'll leave them for now. We are now looking at carbon's valence electrons, which are those that are used for forming bonds. Let's check out how they're arranged. 2 electrons are orbiting in the 2s orbital, and 1 electron is orbiting in each of the 2px and 2py orbitals. As you can see, the 2pc orbital is currently empty. Carbon normally forms 4 bonds, but here, only the 2 2p electrons are unpaired and available for a chemical bond. How can that be? We can get 4 unpaired electrons through excitation of one of the 2s electrons into the unoccupied 2pc orbital. Carbon is now almost ready to form some bonds. Carbon bonds depend on the type of hybridization that takes place in the electron orbitals. Hybridization is where the atomic orbitals mix to form hybrid orbitals. Let's see the different types of hybridization, starting with the most simple one, the Sp2 hybridization. In order to form 4 bonds with other atoms, the 2s, 2px, 2py, and 2pc mix to form 4 equivalent orbitals, called sp3. This is the process of hybridization. The sp3 orbitals form the 4 corners of a pyramid with triangular sides, a so-called regular tetrahedron. The angle formed between the orbitals is 109.5 degrees. With the sp3 orbitals, each occupied with a single electron, carbon can form 4 equivalent single bonds with another molecule, for example, hydrogen. These are called sigma bonds. The angle between the orbitals will determine the angles between the chemical bonds the carbon atom will make. So when forming sp3 orbitals, the angle of the bonds will be 109.5 degrees. A carbon atom can also bind to another carbon atom using a sigma bond. The rest of the sp3 orbitals can then form more sigma bonds with other compounds. For instance, with hydrogen to form ethane, as shown here. Let's have a look at another type of carbon hybridization, sp2. With sp2 hybridization, the 2s, 2px and 2py mix to form 3 equivalent orbitals. The pz orbital will stay intact. The angle between the sp2 orbitals is 120 degrees. The sp2 hybridization is used when carbon forms double bonds, e.g., with another carbon. One sp2 orbital is used for a sigma bond. The pz orbital is used to form what's called a pi-pi bond. Even though the pi bond locks in 2 places, it only corresponds to a single bond. The remaining sp2 orbitals can bind with sigma bonds to other atoms, such as carbon, oxygen, or hydrogen. The bond angle will, as before, be determined on the angle between the orbitals, and will, therefore, be 120 degrees. If only bonds with hydrogen atoms are formed, an ethene molecule is created. Let's have a look at the sp hybridization, the last one for now. In sp hybridization, only the 2s and 2px mix to form 2 equivalent orbitals. 2py and 2pc stay intact. The angle between the sp orbitals is 180 degrees. The sp hybridization is used when carbon forms triple bonds, e.g. with another carbon. As with sp2, a sigma bond is formed using one of the sp orbitals. 2 pi bonds are formed with py and pz. The remaining sp orbitals can form sigma bonds to other atoms. The angle between the 2 sigma bonds will be 180 degrees. If only hydrogen atoms bond, an ethine molecule is formed. That's it for now. Let's go back to the lab for a little quiz to see if you've got this. Let's see if you caught the essentials of the animation. What is the valence value of carbon? Yes, the outer shell of the carbon atom has 4 electrons, so this is its valence value. What orbital hybridization does a carbon atom have that has 4 single bonds? Exactly. With 4 single bonds, carbon's electrons in the 2s and 2p orbitals combine to form 4 equivalent sp3 orbitals. Alright, last one. What is hybridization? You've got this. The hybridization concept allows for the formation of equivalent chemical bonds from inequivalent atomic orbitals. For carbon, this is needed for the completion of the octet rule. Compare the molecules on the hollow table. Interact with the lab pad to continue. Besides methane, you now see two more molecules on the hollow table, formaldehyde and carbon dioxide. Note that the red atom represents oxygen. Can you spot the right statement for methane, formaldehyde, and C oxygen? You nailed it. They all have different bond angles. Bond angles are very important in many reactions in organic chemistry, where they determine the structure of the products. Methane is a hydrocarbon, which means it consists of only carbon and hydrogen. More complex organic compounds contain other elements such as oxygen and nitrogen. Even though carbon dioxide contains carbon, it is not considered an organic molecule, as it does not contain any carbon-hydrogen bonds. As you now know, a carbon with only single bonds forms these at different angles than the carbons with double and triple bonds. Let's explore these differences. Click on the hollow table to go back to the center of the room. Go to hollow table 1 in the middle of the lab. Your mission here is to build the proposed molecules by adding the hydrogen atoms at the correct angle. New hydrogens can be picked up from the left on the hollow table. You can discard excess hydrogens in the trash bin. The molecule can be rotated by clicking the arrows on either side of it. This way you can get a good view of all the suggested hydrogen positions. Let's see if you can identify the correct configuration. Place all the hydrogens in ethane at the correct angles. Interact with the lab pad for hints. Click on the lab pad for more information. Good job. This molecule is called ethane. Let's see if you got the angles right for Sp2 hybridization. When carbon binds to 4 other atoms, what is the angle of the carbon bonds? Indeed, when carbon forms bonds to 4 atoms, it has 4 Sp2 hybrid orbitals that are organized forming a regular tetrahedron structure. This means that the angle between each bond is 109.5 degrees. Alright, can you do the same challenge for propene? Awesome. Can you do it for propine as well? Well done. It looks like you now know the bond angle of each atom depending on the type of compound. I'm sure you also noticed that for each extra bond added between 2 carbons there will be 2 fewer hydrogen atoms in the compound. What is the angle between the 3 sigma bonds made by a carbon with Sp2 hybridization? Indeed, the 3 bonds will be positioned with the furthest distance between them, resulting in a flat, 120 degrees arrangement. Alright, last one. What type of hybridization results in an angle of 180 degrees between the bonds? You've got this. Sp hybridization is exhibited in connection with a triple bond, with the single and triple bond forming a straight line. Like here, with propyne. I think that's everything we need to know about carbon valence, hybridization, and bond angles for now. Let's go see how Simon is doing. Click the hollow table to go visit Simon.
Hey, welcome to my garden party. Dr. One told me everything you found out about carbon valence, hybridization, and bond angles, and it was super helpful. It's amazing. Once you know there are organic compounds everywhere. The barbecue here runs on propane gas, which is a hydrocarbon and also an organic compound. These burgers contain proteins, fats, and carbohydrates, all of which are more advanced types of organic compounds. Anyway, thanks so much for helping out. Now just enjoy the rest of the day.
Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.